Hi, I'm Michael Hicks. I'm a professor at the University of Maryland, and today I'm going to tell you about fuzzing and how to evaluate it. This is joint work with George Cleese, Andrew Roof, Benji Cooper, and Shi Wei, who were all with me at the University of Maryland when we carried out this work. So this talk is based on a paper that we presented 2 years ago at ACM CCS. And in the year that followed, the paper won the NSA's Best Scientific Cybersecurity Paper Award, which is the reason that I'm giving this talk. The paper looks at how potential advances in fuzz testing are evaluated scientifically. And the talk today will cover the content of that paper, which is still relevant, which is how should we scientifically evaluate the potential advances in randomized testing, that is fuzzing. I'm also going to spend some time looking at the impact of the paper since it was first published. It's been 2 years. How have things changed? So to begin, let's talk about what fuzzing is. It's a kind of testing based on random input generation, and the goal is to make sure that certain bad things don't happen no matter what. So crashes, thrown exceptions, hangs, all of these are bad, and they potentially have security ramifications. Fuzz testing is a complement to normal functional correctness testing, not a replacement for it. Let's consider file-based fuzzing, which is the most common form of fuzz testing still today. It works by starting with an input that it will either mutate or generate, and then it will run the target with that input and see what happens. Perhaps the input was provided as a seed and the fuzzer then mutates it, and then perhaps the program crashes and we found a bug. A very popular fuzzer used today is American Fuzzy Lop, or AFL. It's a mutation-based gray box fuzzer, and it's gray box in the sense that it looks partly at what the program does to determine how it should respond in generating new inputs. The way that it works is it instruments the target program to gather information about code coverage, which it does using a tuple consisting of the current code location and the ID of the last code location. It will then retain a generated test input to create a new one if the coverage profile based on that gathered information has been updated. So for example, I could compile my program with instrumentation using AFL GCC. I could then run the AFL Fuzz program on my target program, and then let it do its thing. And AFL has a nice runtime display as well. Now, fuzzing is an active area of research. There are many different kinds of fuzzers. So black box fuzzing is a sort of fuzzing that only generates inputs and knows nothing about the internals of the target program. Gray box fuzzing is of the flavor of AFL, like I just mentioned, and there are many varieties. So-called white box fuzzing does even more to see what the internals of the program are doing, for example, by performing symbolic execution. And then there are hybrid approaches between gray and white box. And there are many others that aren't listed on this slide. Okay, so given that we have so many options for fuzzing, we might imagine that it's clear which one is the winner. To do that, we need to assess our progress. We need to know that claims that support that one fuzzer is better than another in some aspect are actually justified by scientific evidence. And of course, papers provide this evidence. The question is this evidence reliable? So here's a recipe for evaluating your fuzzer. Let's call that fuzzer A. To convince me that your fuzzer is making an advance on the state of the art, we begin with a compelling baseline fuzzer to compare against. We then need a sample of target programs, a benchmark suite, that represents a larger population. We need a performance metric, which is when we run the fuzzer on these target programs, how does its performance differ from that of the baseline to show that it's better? We need a meaningful set of configuration parameters, for example, seed files and a timeout, to set the stage for these experiments. And finally, we need a sufficient number of trials to judge that the performance is consistent and not an outlier. And this is because fuzzing is a random process. And as such, we should also be performing a statistical test to show that even after some number of trials, we have high confidence that our fuzzer is better than the baseline. Now, to assess progress in the scientific evaluation of fuzz testing papers, we looked at 32 papers from 2012 to 2018 and compared their evaluation using our template. We looked at what target programs, seeds, and timeouts they chose, and against what baseline they compared. We also asked how they measured performance, how many trials they performed, and what statistical test, if any, they performed as well. What we found is that most papers did some of these things right, but none were perfect. and that raises questions about the strength of the published results of those papers. Now, of course, it could be that failure to follow the template doesn't mean that the reported results are wrong. It just means there is a potential for them to be wrong. So we wondered, well, how close is that potential to reality? So we carried out some experiments to assess it. And based on our experiments, indeed, we find that there probably are problems with existing evaluations. And so we provide some recommended mitigations to avoid these problems in the future. Here's a summary of our results. First, less than half the papers we considered measure multiple runs. Fewer still considered even the variance across those runs. And yet, of course, fuzzer performance can vary substantially from run to run, and so this is a dangerous practice. We also found that papers often choose a small number of target programs with a small common set between them. Of course, they're trying to target the same population, but superficial or important differences between those programs could cause the performance to vary, and indeed we found this in our experiments. Few papers justify the choice of the seeds or timeouts they use, and yet we found that these can strongly influence performance and that trends can change over time, meaning that an over short timeout may fail to capture the performance profile of a fuzzer. Many papers also use heuristics to relate crashing inputs to bugs, and yet these heuristics themselves have never been fully evaluated. So we wondered, are the heuristics actually a true measure of bugs? And what we found was, at least in one case, they could dramatically overcount the number of bugs. Now, all of these problems seem bad, and you might wonder, don't researchers know better? Shouldn't they be doing a better job of carrying out a scientific evaluation? And I would say, because most of them do some of the things right, they do. But as we've all probably experienced, experts can forget to do the right thing from time to time, and a culture needs to be in place to push them towards doing the right thing. So one solution to this is to create a list of recommendations and the identification of open problems. And this so-called checklist manifesto, the list of recommendations, is advocated in the field of medicine as well. So around the time that we were working on our paper, I spearheaded a committee as part of the special interest group on programming languages to create an empirical evaluation, a set of empirical evaluation guidelines. I should say I initiated the committee, but Steve Blackburn was the chair, and Matthias Hauswirth and Emery Berger were also members. Okay, so here's the outline for the rest of the talk. I'm going to talk first about the papers we looked at and the categories we considered, go into more detail about what I just presented. And I'm also going to talk about our experimental setup for the experiments we did. I'm going to then present the results by the different categories that I discussed before: statistical soundness, seed selection, timeouts, performance metric, and benchmark choice. And I'm also going to talk about how things have changed from 2018 to 2020 and to talk about where we are in these categories. Okay, so let's start with the papers. We looked at 32 papers from 2012 to 2018. We started from 10 high-impact papers that were published at top conferences and were well cited. And then we looked at citations to those papers, and we performed a keyword search to hunt around for relevant papers. Now, these papers, while all being about fuzzing, had disparate goals. Some were about improving seed selection. Some wanted smarter mutation. Some were concerned about things other than crashes or failures. They might care about runtime. Some looked at increasing execution time speed, and there were many others. But they were all common in the sense that they were running a fuzzer and saying that it improved on the state of the art. Now, for the experiments we carried out, we compared one advanced fuzzer, AFL fast. This is our A in that setup for comparison, and the baseline was AFL. For our benchmarks, we used 5 target programs previously targeted by previous fuzzers, and 3 of these were from bin utils, and 2 were image processing programs. We carried out 30 trials, more or less, sometimes a few less, and we ran for 24 hours per run. And we tried different seeds, the empty seed. We sampled seeds from a pool of seeds and took some other approaches. And we used the Mann-Whitney U-test for our statistical test. We also carried out experiments on deduplication effectiveness. Now, I want to emphasize that our experimental evaluation is not necessarily meant to be representative of a proper evaluation. Rather, it's meant to help expose potential problems in evaluation practices that occurred before. When I get to the end of the paper or as I go, end of the talk or as I go, I'll say more about what an ideal evaluation would look like. Okay, so that covers the original paper. Since 2018, there have been many more papers published about fuzzing. So I took some time to look at 15 papers that were published over the last 2 years in top conferences. I'm sure that I missed some, but hopefully I'm not too far from capturing the core kernel of advances there. And I compared these papers against the same criteria that I laid out in the Evaluating Fuzz Testing paper. So the question is, the paper's been out for 2 years. How is new work responding to that? So I'm just going to briefly flash up this table. You can see the names of the systems there along the left-hand column, and the venue, IEEE Security and Privacy, Usenix Security, ICSI, and so on, and the year that those papers were published. And then, of course, all of the same sorts of categorizations that were from the original Evaluating Fuzz Testing paper. So I'll explain what this table looks like as we go. Okay, so for the first topic to consider, let's go into statistical soundness. Now, fuzzing is a random process, and the mutation of an input is chosen randomly by the fuzzer, and the target may make random choices. Each fuzzing run, therefore, is a sample of that random process, and the question is, did that process yield a crash, a failure, or not? So a sample, a run, can be used to approximate the distribution of the fuzzer's overall ability and performance. And more samples will give greater certainty that we've captured the true representative performance of the fuzzer. So to answer the question, is A better than B at fuzzing, we need to compare distributions to make that statement. We can't compare, for example, individual runs or individual samples. We have to look at overall behavior and compare the overall behavior of A and that of B. So let's consider the analogy of biased dice. I want to compare the performance of 2 dice and ask whether die A is better than die B, which I'll say that it is if die B tends to land on higher numbers more often. That is, it is favorably biased. Now, suppose rolling A and B yield 6 in 1. Is A better? Well, it's possible, but we don't actually have enough information. One trial is not enough to characterize a random process. So, well, what if I roll A and B 5 times each? And I get 6, 6, 1, 1, 6, and 4, 4, 4, 4, 4. Is A better? Well, one way that we could perform the comparison is we could compare average measures, like the median or the mean. By the median, it would seem that A is better. By the mean, it seems like maybe A and B are the same. And there's still uncertainty that these comparisons hold up after more trials. Maybe if we roll A and B 5 more times, they will start to separate in some way. So this is what statistical tests are for. They're a mechanism for quantitatively accepting or rejecting a hypothesis about a random process. In our case, that process is fuzz testing, and the hypothesis is that the fuzz tester A, which is a random variable, is better than B at finding bugs in a particular program. So our hypothesis might be, for example, that A minus B is greater than or equal to 0. The confidence in our judgment is captured by a so-called p-value, which is the probability that the outcome of the test is wrong. And the convention is that the p-value being less than or equal to 0.05 is a sufficient level of confidence. Now, there's some debate about the value of p-values and whatnot, but it's still a useful tool for comparing 2 random processes and seeing how far apart they are. So now the question is, well, which statistical test should we use? And to answer that question, we use this ICSI 2011 paper as a guide. Rather than use a test that I learned in my statistics class many years ago, the student t-test, this paper recommends that you use the Mann-Whitney U-test. And the reason being that it makes no assumptions about the distribution of the samples that you take, the distribution the samples are drawn from the 2 fuzzers. In particular, the student t-test assumes a normal distribution, but it seems very, very unlikely that you'll get a normal distribution of fuzzing run outcomes. Okay, so now let's look at the actual papers and see how they did. Here's that table again. There are 32 papers, 1 for each row in the table, and I've highlighted the parts of the table that capture this question of statistical significance. Now, the first thing to see is that the trials column is almost as empty as it is full. That is, 17 out of 32 papers said nothing about running multiple trials. And based on context clues in the paper, we assume one run. 15 out of 32 papers said multiple trials, and as you can see, there's a widely differing number of trials across those papers. 3 out of 13 papers characterize the variance across the runs. That is, did you get a widely differing performance outcome with each particular run, or did you not? And even though some papers claim multiple trials, they didn't say very much about, at least quantitatively, about the difference. And no papers performed a statistical test. Okay, so maybe that seems bad to you, maybe it doesn't. One reason that it might not is that you might be thinking, well, fuzzers run for a long time, and they conduct potentially millions of individual tests over many hours. So if we think of a fuzzing run as millions of die rolls, perhaps there's no statistical comparison needed. That is, that we've done so many random tests that all of the randomness kind of cancels out. The problem with this line of thinking is that fuzzing is a stateful search process. So each individual random choice made during a fuzzing run is not independent. That is, rather the next input is influenced by the prior input, which is influenced by the coverage information from that particular test. So really what's happening is we're doing sort of a randomized walk across a very vast search space, and covering all of that search space is going to be difficult. And indeed, the different paths through that search space may be very different. Therefore, we should really consider each run as a trial, and then consider many trials. As it turns out, this is going to be really important for fuzzing because we found in our experiments that there is a high per-trial variance. Okay, so have a look at this plot. This is showing the performance of AFL and AFL fast. The x-axis is time, so as time goes by, we move from left to right. And the y-axis are crashes found according to AFL's uniqueness criteria. And so what we can see is that over time, the number of total unique crashes is going up as the fuzzer is allowed to run longer. The solid line is the median, and the lightly dotted lines are the max and the min, and then the thickly dotted lines are the 95% confidence interval in these plots. And we have the same thing for both AFL and AFL fast. Okay, so looking at this, that prior example, and looking at this present one, another one, that was NM, this is now also CXX fill, we can see that AFL fast is doing significantly better than AFL on these particular benchmark programs. In particular, there's a significant variance in performance that's pretty solid. The higher median is clearly better for AFL fast than AFL. And if we do the Mann-Whitney statistical test, we say that that difference holds with high confidence. That is, there's a very small p-value. Now, on the other hand, this difference did not hold between AFL and AFL fast on every benchmark program we considered. So in particular, FFmpeg and GIF to PNG, the p-values were not in the less than 0.05 range. For FFmpeg, they were almost identical in terms of performance. And for GIF to PNG, it looks as if AFL fast is doing a little bit better, but not nearly as much better as in NM and CXX fill. Okay, so the takeaway here is we should really run multiple trials and use a statistical test to compare distributions to make sure that the differences we're seeing are indeed significant. Okay, so that was our advice in 2018. How are things in 2020? They're looking a lot better. So at the 15 papers I considered, essentially all of them used multiple trials. Only one was a little bit vague about what a trial was, and that's the Superion paper. But every other paper used at least 3 trials, typically 5. And most papers reported the variance or as a marked difference to the papers before, used a statistical test. And many of them used the Mann-Whitney U-test and cited our paper for the reason for using it. 2 papers didn't say which statistical test, and 1 paper also used the A12 effect size test. So this is a definite improvement over the way things were, and that ought to give us more confidence that the results being reported in the last 2 years are more likely to hold up, at least due to this criteria. Okay, next let's talk about seed selection. So mutation-based fuzzers require an initial seed or seeds to start the process of fuzzing. We take that initial seed, and then the fuzzer will mutate the seed, feed it to the target program, decide whether to keep the seed or not, and then mutate the next seed, provide it to the target program, and so on. Of course, this process carries on by itself once we get going, but the question is, what should be the initial seed or seeds to drive the process? Now, the conventional wisdom is that you want to provide a valid input. For example, if you're fuzzing GIF to PNG, you provide a valid GIF file, but you want to make that input small so that individual tests, runs of the program, don't take too long. The reason for validity is that you want to drive the main logic of the program and get past that pesky format checking, and therefore get into the sort of guts of the main part of the program. So there have been some studies that suggest how to prove seeds, how to choose seeds, but these have mostly been applied to black box fuzzers. And the question is, are they relevant to gray box fuzzers or white box fuzzers, for example? A broader question is, how might the seed choices matter in terms of comparing the performance of two fuzzers? Does it really not matter? Does any seed represent the behavior of one fuzzer compared to another? Or might the seed choices make a difference? So looking at the evaluations, the 32 papers, we can see that 30 out of 32 used a non-empty seed. So 10 of the papers say nothing about what that seed actually is, and 9 used a seed that they said was valid according to the expected input format of the program. 2 out of the 32 papers used an empty file as a seed, and this is interesting. This is a good default choice in the vast configuration space because, in some sense, every target program, no matter what input format it expects, should be able to deal with an empty file. And it's kind of the baseline of a bootstrapping process for a particular fuzzer, how it deals with the empty file. But this turns out to be obviously contrary to practice. Only 2 out of the 32 papers did it. Okay, so let's see what the experimental impact of seed choices were to shed light on this decision that these papers are making. So we carried out a bunch of experiments, again, between AFL and AFL Fast, and we used the empty seed as well as seeds sampled from the FFmpeg site or sampled from, say, object files and other files on the file system for use with NM and object objdom. We also constructed seeds with FFmpeg itself using some of its own programs. And these seeds were given to FFmpeg and also to GIF to PNG. Okay, so here are 2 charts showing the impact of, on the left, using the empty seed with FFmpeg, and on the right, using a single made seed, one seed, which was made by using the FFmpeg program. Now in these charts we have AFL Fast and AFL once again, but we also include what we call AFL dumb, which is to simulate a black box fuzzer, and it does not use any coverage information, it just uses straight up mutation. Okay, so on the left-hand side, we see that AFL Fast and AFL have virtually the same performance. The statistical test does not distinguish them, but they are, AFL is definitely better than the dumb black box fuzzer. And in fact, you can't even see the line. It's there hugging the x-axis on the chart on the left. Now on the right-hand side, for the handmade seed, we see that the p-value between AFL Fast and AFL is close to statistically significant. You just can't see it very closely because the difference between that and AFL dumb is enormous. The p-value is tremendous. And this in and of itself is somewhat shocking that a black box fuzzer would do so much better than a gray box fuzzer with this particular choice of seed. Okay, so here's another chart, this looking at FFmpeg once again, where we're looking at sampled seeds, that is pulled off of the FFmpeg website, and a seed that we constructed ourselves. So this chart on the right is the same as the one that we saw on the prior slide, and the chart on the left is using the sampled seed. And once again, we can see the performance here is dramatically different between these 2 situations. On the left, we have only 5 crashes, but on the right we have close to 100 crashes. Okay, so the takeaway here is, putting AFL dumb aside, Both of these are valid seeds, but they have very different performance. Okay, so what does all of this mean? The performance with different seeds varies dramatically. AFL dumb, when given one kind of seed, had terrible performance, and with a different seed had dramatically better performance. And AFL and AFL fast also had dramatically different performance on the same target program when given a different seed, even if the seeds were valid in both cases. Okay, so the conclusion here is not all valid seeds are the same. Some can promote better or different performance than others. Another interesting thing is the empty seed can perform well. We actually saw pretty good performance on FFmpeg, despite the conventional wisdom saying you shouldn't use empty seeds. So our recommendation is that evaluation should really document their seed choices, not just say, oh, we picked some random seed and we won't tell you what it is. And indeed, I think that we should expect evaluations to consider runs with several distinct seeds, including the empty seed, because essentially the seeds are another large random space that affects the performance of your fuzzer. Depending on which seed you start with, you may have very, very different performance. And you want to help researchers choose seeds that are going to show that no matter how their tool is used, it's going to do better, say, than a baseline. That said, that's easy for me to say. I think the seed space is one of the large unexplored areas of fuzzing research, and we need a lot more to understand this phenomenon better. All right, so fast forward to 2020. What is the situation with seeds? Frankly, we can see that things are pretty much the same as they were before. I found in looking at the papers that once again, there was a little bit more attention paid to describing what seeds were used, but typically not very much attention paid to why that seed made sense, or even with experiments with multiple seeds to confirm that the performance trends were the same. And as I say, I think the reason for this is that we just don't have a good idea yet of how seeds affect performance, and we need more research there. Okay, let's move on to timeouts. When you run your fuzzer, you have to decide how long to run it and when to stop running it, and at that point to make a performance comparison. So how long did existing papers run their fuzzers? Well, 10 out of 32 ran for 24 hours. That was the most common. 7 out of 32 ran for less, 5 or 6 hours. Some ran for far less, and some ran for far more, even days or months. So the question is, how much does this choice matter? That is, if we looked at the performance at 5 hours, at 12 hours, at 24 hours, or at 2 months, are they all basically going to show the same trend, or are the trends potentially going to reverse? What we might hope is that trends are stable, that as a fuzzer is moving along its crash-generating trajectory, that trajectory is going to stay roughly on the same tack, and maybe it'll level out over time as more and more of the program is explored. So here for NM and CXX Filt, we can see that AFL fast is definitely better than AFL at 5 hours, at 8 hours, and at 24 hours. However, this is not always the case. In this run here with NM, with 3 sampled seeds, we see that AFL fast is better at 6 hours, but then AFL overtakes it at 24 hours. And again, this is not just a one-off run. This is for 30 runs between the two programs. We can see those medians are diverging. Okay, so there is some risk at choosing an earlier timeout when, because it may be that much of the program's sample space, search space, has not been explored yet. So what this means is that longer timeouts are better because they subsume shorter ones. If you use plots like the ones that we've shown before, the performance can be compared at different points in time, say at 5 or 12 or 24, which can then give users more information about deciding when to use a particular fuzzer, right? For example, maybe one that claims to find bugs faster, but not as many bugs overall. On the other hand, of course, there's a practical limit to long timeouts. We don't have unlimited machine resources, and it might be that waiting a long time on limited resources is going to mean a long time to carry out our experiments. So we have to pick some reasonable end, and maybe 24 hours is a good target. It seems ecologically relevant. You'll be willing to run your fuzzer for a day. Maybe longer is better, running for a week is better, but it at least subsumes the 5 and 8 hour time limits. Now, I admit we chose this limit because it was the de facto choice amongst the papers that we looked at. It was the most common. But it does seem like there are potential reasons for it that make it useful, and maybe that's a good thing. So in 2020, it seems that many papers are doing this also. Maybe they're taking our advice. Two papers fuzzed for a really long time. One, 72 hours on 88 processors in parallel, and another, the Symposium paper, for 3 straight months. Okay, so up until now, we have been talking about performance in terms of numbers of crashes produced. And the reason that we do this is that we're thinking about bugs, that if your program crashes, that means you found a bug. Now, the thing is, it may be that multiple crashes are the result of the same bug. It might be that there's some flaw in our program that once we fix that flaw, many of the inputs that produce the crash will no longer produce the crash. So ultimately, what we really want is bugs. Now, some benchmarks are designed so that it's clear that there is a particular bug that's being triggered by a run, that the crash is a telltale sign. But for others, if you're just picking a real-world program, how can you tell which crash signals which bug so that you can disambiguate crashes and bugs? Now, there's 2 basic heuristics that people use to try to answer this question. One is called the stack hash, and the other is code coverage, or AFL-CMIN. If we look at our evaluations, we can see here in the crash column that 7 used AFL-CMIN. This is the so-called unique crashes metric, and 7 used stack hashes. 7 of them were able to assess ground truth perfectly, and 8 others did in part by doing some manual triage after the fact. So given that the crashes and stack hashes are common metrics that are used to compare fuzzers, we might ask how effective they are at correlating, that is predicting ground truth. Right, what we would hope is that, yes, we ultimately want to find bugs, but we would like to believe that a tool that's better at finding unique crashes or unique stack hashes than another is also better at finding bugs. So we can use the latter as a proxy for the former. So let me say a few more words about what these things are, stack hashes and coverage profiles. The idea of a stack hash is pretty intuitive. You want to identify a bug in accordance with the stack at the time of the crash. So basically you can look at the return address, for example, at the top of the stack to know what instruction, the program counter, and maybe the return address at the top of the stack to know the function and the line number on which the crash occurred. Maybe you want to limit your attention to just that instruction, but maybe you want to look at the whole stack or some subset of frames. The rationale is that the faulting location is indicative of the source of the bug, whereas the stack provides useful context. But maybe some context is superfluous, so we need to look at just the most recent context. So here's a program that kind of illustrates what's going on and the potential dangers of using stack hashes. So we have 2 functions, f and g, and those 2 functions call the format function, and they each pass a different string, s1 and s2. Now let's say that the source of the bug is in the format function. It's going to corrupt s in some way, and then pass it to the prepare function, which then passes it to the output function. And at that moment, the failure is going to manifest. If the corruption introduced by format, that is the real source of the bug, manifests in the output function when finally it has a look at that string that was corrupted. Now, with n is 3, distinct calls, that is, we look at the top 3 frames, distinct calls to format from f and g will be properly conflated. That is, we'll only look at format, prepare, and output on the top of the stack, and whether we called from F or we called from G, we'll know that those 2 things represent the same bug. They have the same stack hash, crashing on the same line with the same top 3 return addresses. On the other hand, with n is 5, calling format from F and G are made as distinct bugs. So now, because the stacks differ, on one stack we have F, the other stack we have G, we think of those 2 things as different bugs, and so we're overcounting. On the other hand, with n is 2, a bug in a different caller to prepare that corrupts its argument will be conflated with the format bug, right? So let's imagine we have some other format true, format x function, and inside of that function we corrupt s as well, and then call prepare and output. In that case, we have 2 distinct bugs, but we'll only see the prepare and output calls on the top of the stack, and we'll conflate those two things as the same bug because they have the same failing location in the same stack. And in that case, we're undercounting the number of bugs. There's different root causes, but the same manifestation. Okay, so AFL CMIN is a different approach. It distinguishes bugs based on a so-called coverage profile that includes all of the tuples, the edges that were seen during the run that produced the crash, right? So given a particular input, the coverage information that's gathered by AFL will represent sort of a signature for that particular run, and distinct signatures will be considered as distinct bugs, roughly speaking. Now, while CMIN is unlikely to undercount bugs, it is very likely to suffer from inflated counts. In particular, that same problem we saw with both F and G being considered different bugs because they happen to call the code that was the source of the problem would just as easily happen with CMIN. In fact, might happen more often, where you have distinct stacks, but you have common coverage profiles. All right, so to assess these heuristics, we use the CXXFilt program, and we looked at all of the 57,000 plus crashing inputs that were produced by AFL and AFL Fast when fuzzing this program. These inputs are after CMIN processed them, and we just merged together in a giant pool the results from all 30 runs. And what we did was for each of the versions of CXXFilt since the fuzz version, we applied a patch, and then we reran the patched version on all of the 57,000 crashing inputs. Some of those inputs don't crash anymore because the patch fixed the bug that was manifest as that crash. So for all of those inputs that no longer crashed, we attribute them to the same bug. And that's what gives us a nice assessment of ground truth. Now, sometimes these bugs manifest due to non-determinism, and so to limit that, we used ASAN and UBSAN to identify the root cause of the crash, rather than sometimes what might happen is you would overrun a buffer and then some random time later it would crash. Here we're able to isolate things more deterministically. Okay, so given this ground truth, we assess the efficacy of stack hashes and CMIN. All right, so let's start talking about stack hashes. First of all, let's talk about the ground truth measure. We can see for the first column that there were a total of 9 bugs that corresponded to most of the 57,000 inputs. 98 of the inputs were never actually fixed by patches we could find, and 4 of them seemed to be fixed, but we could not nail down which fix it was due to non-determinism. If you look at the far right column, you can see input count. And for example, for bug A, 228 inputs were fixed by when bug A's patch was applied, 31,000 inputs were fixed when bug B's patch was applied, and so on. Okay, so the middle 3 columns now look at the efficacy of stack hashing, and we chose n equals 3 for our stack hash. So first of all, we can see that in general, there's far less overcounting. If the input count on the right is the result of CMIN, the number of hashes is a dramatic reduction in most cases of that, right? So for example, bug B has 362 hashes, whereas it has 31,000 inputs. Okay, so that's a whole lot fewer hashes to overcount bug B. And in general, 596 total hashes overcount those 9 bugs a lot less than 57,000 inputs do. Now, on the other hand, hashes, the second column, also have false negatives, and those are shown in the 4th column, so-called false matches, right? And the idea here is that a particular hash matches not just the manifestation of the bug on that particular row, but also happens to match a bug on a different row as well. Okay, so for example, bug B has 343 hashes that apply just to this bug, but 19 false matches that apply to other bugs too. Okay, and the idea is if we thought that a particular input was just a duplicate of something else because it had the same stack hash, we might throw it away. But as it turns out, 19 times out of 362, doing so would have thrown away evidence of another bug. It would have, that false negative would have made it so we did not find and fix a mistake. So false negatives are bad. Now, if we, an interesting thing to do is to say, let's look at CMIN, and instead of comparing the performance of AFL and AFL Fast according to unique crashes, as we have been doing throughout this talk, we compared it based on bugs found, then how would things look? So this chart shows the mapping of bugs, inputs to bugs for the two programs. On the left, AFL, and on the right, AFL Fast. Each bar here represents one of our 30 trials, and each color making up the bar is a distinct bug. So remember that we saw that bug B had so many inputs associated with it. Well, that's the red bar, the red portion of each of these bars. And there are other very popular bugs also, which are making up most of the chart. Okay, so if we look at the left side and the right side, and we just do bug counting, we can see that AFL Fast is definitely finding a whole lot more inputs than AFL. That's the trend we saw before. The bars are all higher. The question is it finding more actual bugs? And if you look at the numbers on the tops of the bars, the answer is only a little. That is, the far left side of each of the set of bars is 5 bugs. The far right side is 8 bugs. And in fact, no particular single run found all 9 bugs. If we apply the Mann-Whitney U-test to compare the bugs distribution rather than the crash distribution, we actually find that the number of bugs that is not statistically more for AFL Fast than for AFL, even though when considering unique crashes, it's it's very clearly statistically significantly different. Okay, so what does this all mean? This is just one program and one set of fuzzing results, but it shows the potential for heuristics to massively overcount bugs and to miss bugs. Okay, it's experimental evidence of this. Fortunately, it seems like the situation is tilted toward overcounting rather than undercounting bugs, and so we can try to whittle away to get better. We don't have to worry about missing things. As such, it seems really important if we want to determine that one fuzzer is better than another to measure ground truth directly. And to do that, we need to use benchmarks with known bugs and not just rely on these heuristics. If you're going to use other programs, that's fine, but you want to have some baseline where you have known bugs that you can compare them with. So fast forwarding to 2020, things are better. 14 out of 15 papers results are now based on some significant assessment on ground truth. So at least part of their benchmark uses a ground truth determination. Now 10 of the 15 papers also use some form of unique crashes, and interestingly, most of them do not just rely on AFL-CMIN for their unique crash determination. They will do extra work to avoid overcounting. Some do rely on stack hashes, usually just the topmost stack frame, not n equals 3, but n equals 1. But even there, they do a little bit of extra work to disambiguate. Unfortunately, it's different from paper to paper, so again, it makes it hard to compare what this stuff means across papers. But as you can see as well, there are a lot of baselines that this more modern work compares against, so at least even internal to that particular paper, there's more that we can say. I should also point out that 11 out of 15 measured code coverage as a proxy for bug finding ability. That is, if the fuzzer could reach more parts of the program, maybe it's better than another fuzzer, and that's captured in the column to the right of crash, and you can see a good proportion of the programs do that. This is not something we spent a lot of time on in our paper, but I do think it makes a lot of sense to consider this metric. Okay, so the last thing I want to look at is target programs. What were the programs that the fuzzers were applied to when assessing their performance? So 30 out of 32 used real programs. Usually about 7 were picked. Some, in one case, as many as 100 programs were picked. 2 out of 32 used the so-called Google Fuzz suite, which is based on real programs. Now, the big question one always has in this circumstance is were those programs representative or fair when so that they can be compared safely, the results can be compared across papers. We'll get to that. 9 out of 32 of the papers used purposely vulnerable programs or injected bugs. So 5 used the so-called Lava M benchmark, and 4 used the CyberGrand challenge. And the question here is that are artificial programs representative of real programs in terms of their bug distribution? So according to our experiments, we tried to look at programs of a different flavor. So on the left is NM, it's a object file processing program, and on the right, it's a image processing program, FFmpeg. And we can see that the performance on these two programs of the same two fuzzers is very different. So, if we only looked at the bin use tools program, which actually shared a lot of the same code, we come to one conclusion with AFL fast. But if we had also included in that paper the FFmpeg program, the results would not have looked quite as good. So it's important to have a diversity of programs in your benchmark suite. Now, what about these artificial suites? The Google Fuzz test suite has 24 programs and libraries with known bugs in them. That's good, ground truth. And it comes with a harness to connect to AFL and libfuzzer, Google's fuzzer, and it will confirm when a particular bug is discovered. So this is nice. You can use the Google Fuzz suite to see that your fuzzer is able to find a particular bug. However, as it turns out, the Google Fuzz test suite is kind of a regression suite. It just has, it's not really set up for exploratory fuzzing, and so its generality is not so clear. Google also has the open source Fuzz project, where a bunch of open source projects are constantly being fuzzed by libfuzzer and Google's fuzzers, and the bugs are reported back to the maintainers so that they can fix them. Maybe programs from this Fuzz suite would be good for evaluation. The Cyber Grand Challenge was a DARPA-sponsored event a few years back, and a bunch of programs were artificially constructed for the basis of the competition. They were intended to be ecologically valid, but this hasn't been assessed empirically in any way. Several of the papers used the Cyber Grand Challenge, actually a port of it, to assess their fuzzing performance. And again, a good feature here is known ground truth. The question is just, are these ecologically valid? Lava M is a bug injection methodology that adds so-called magic number checks to inputs and otherwise doesn't affect control flow. And actually that's the Lava is that methodology. Lava M is a benchmark suite of 4 programs modified by Lava with a ton of injected bugs in them. And several papers have used Lava M to assess their fuzzers. Basically, to see how many of those injected bugs a fuzzer can find, since the bugs can be distinguished. So in late 2020, standard benchmarks are in far greater use. 7 out of 15 papers use Lava M. That's good. It has ground truth. The Google Test Suite and Cyber Grand Challenge as well. So that's helpful that they do that. Many of these programs don't just rely on Lava or Google or Cyber Grand Challenge. They also have real-world programs. That's the R in the column. And these are often diverse, and they're selected from programs that were used previously, which is great because now you can compare them against prior results. So as it turns out, since our paper was published, Google has come out with something called Google Fuzz Bench. And in fact, they cite our paper and the follow-on SIG-Plan guidelines as a reason for wanting to create this benchmark suite in the first place. The way that it works is that the researcher is able to upload their fuzzer to Google Fuzz Bench, and the Fuzz Bench will incorporate the fuzzer into their service and produce reports on a per program basis. So this report that we see here in the lower left is capturing code coverage on a particular program for each set of fuzzers, and it shows confidence intervals over multiple trials. Okay, so there are 21 programs. Many of these programs have known bugs. They've had bugs in the past, and the benchmark suite connects to many of these fuzzers already. You can see scripts in there to connect to different legacy fuzzers. It does 20 trials over 24 hours, and it measures edge coverage. Now, the thing that's missing is measurement based on ground truth bugs. If you read the FAQ, the Google Fuzz Bench folks say that they plan to add it, which would be great. But it leaves open the question of how do we get bugs into those programs so that we can measure based on bug finding and not just coverage. Okay, so I want to sum up. When you go to evaluate your fuzzer, you should treat it as a random process, and therefore you should use multiple trials and a statistical test to compare your fuzzer against a baseline. Don't use heuristics as the only performance measure. Some results should be based on ground truth. Clarify your choice of seed, and indeed evaluate several seeds, including the empty seed. Use a longer timeout and measure performance over time so that we can see how trends change. And use a good benchmark suite, perhaps contribute to Fuzz Bench and continue to encourage them to develop it further, using it for your future assessments. And for general guidelines about empirical evaluations, I definitely encourage you to go check out the SIG-Plan guidelines which more broadly speak about empirically assessing things that security researchers do all the time. Okay, thank you for your attention.